So I recorded this video yesterday, and after composing the final version, I realized that 2 hours is way too long for any kind of intro. So uh, I decided to record a prequel to this intro, an intro for intro. And that's what we are going to start with. So what you see here is how Redis performs on my machine. It's 120,000 calls per second. And let's think of this number as a baseline, right? You can run this benchmark in any Redis container. The utility is called Redis benchmark. So 120,000 calls per second. And that's the number you are expected to get with Fusion on the same machine. It's kind of similar one, 130 million calls per second. And that's if you use Fusion's client. So it's 1500 times speed up. And if you use Fusion just on the server side, so without its client, then the speed up is going to be about 20x. And by the way, notice that this number, I mean, almost 90,000 calls per second, it's pretty similar to what you saw for Redis. So in this case, the underlying storage is Postgre. And yeah, obviously, when there is not a lot of data, then they are supposed to produce nearly the same kind of results. Okay. What you see here is even crazier. So the data on the right, or like the traffic over WebSocket connection on the right, shows that Fusion client is managed to resolve 6 calls using a single round trip to the server. So first two messages are a part of handshake, and basically one is outgoing and one is incoming, and 6 calls are resolved. So why 6? Well, we need some data to resolve a user from session and show this piece, right? Then 1 call is for summary and 3 calls are for this part. The first one gets the list of IDs, and then like 2 more calls gets the data. And I think what's weird is that there is a clear data dependency, right? So for example, you need to get the IDs first, and only after that you can get the items by these IDs, or like to get this whole piece of data, you probably need to authenticate first. So how it's possible that this thing manages to kind of pack all of these calls into a single packet and get back the data, right? And yeah, right now I'm going to prove you this. So that's the real code of UI component that renders the list of items, and basically all it does is it gets the list of IDs and well, puts them into a model, and like when the model is rendered, so the next component, that's the component that renders the item. It gets the data for the item by, well, basically its ID. So as I said, there is a clear data dependency. Nevertheless, what you saw is like it's real, a single round trip to the server. So you may think that this is kind of fictional scenario, right? And it's a small sample, but that's the real app, ActualChat, the app that we built, and it's built on top of Fusion. So it sends around 1,300 calls when it starts or reconnects, at least for my account, right? I have a decent number of chats and stuff like this, and it needs approximately 15 messages to kind of get the data for them, typically. And it's just 10 kilobytes of data on reconnection. And yeah, it supports offline mode as well, which doesn't require any extra code. So basically, if you start without internet connection, it's still going to render nearly the same stuff. And that's the code from ActualChat. You can instantly spot that the code looks weird, right? I mean, okay, like stuff like this, you maybe can run it locally, but like it doesn't seem like you can do this with on the client side, assuming that most of these calls are going to the server side and like basically trigger some kind of RPC. Nevertheless, that's the real code, and moreover, this code like actually so it triggers one of frequent animations. I'll talk about this a little bit later. So that's the repository. That's where Fusion lives. And the original, so originally it was called as Stl.Fusion. I started the project while I was a CTO at Service Titan, and I think I left during 1 year after that. I contributed to the original repository for the next, I think, couple of years, but then we decided to basically start maintaining our own fork, and that's the address of the fork. Yeah, the reason why it happened is like I was basically the like almost exclusively the only contributor there, so it makes sense actually. Now, I'm also known for some posts on Medium, a fancy comparison of Go versus C#. I mean, in reality, it's very in-depth comparison. So if you are interested, then definitely check this out. And like most of my posts are kind of circling around performance and .NET. So as I said, I'm also known as a creator of ActualChat. It's a fancy chat app that allows you to talk in like really talk, and we provide both instant transcription and deliver your voice. So basically every chat is kind of like a walkie-talkie where people can talk but don't have to listen all the time. Yeah, they can join at any moment, continue conversation by typing or just telling what they want to say. Okay, and I think we bet on one simple thing that like many people actually don't like to type. I mean, think about your grandparents or like young children or situations where it's just not convenient to type, right? And we basically mix these two experiences into a single medium, typing and talking. There are a few different versions of this app. You can download any. And in any other sense, it's more or less like a normal chat. It should be a good fit for like either family chatting or like a small team where conversations are frequent. Okay, and now we are going to see the first demo, like the first example. So that's how actual chat works. You press this big recording button and start talking, and everyone else who sees the same chat, they see the transcription and can listen to what other person says. But like in reality, if you want to respond, you typically just respond, and that's it. So I'm going to talk about this little button. You see it's spinning right now. Probably, I'll have to replay this part. So this little button, it spins when someone else talks in the chat in the chat you are in, right? So it's a Fusion component, and all of them inherit from computer state component. The model is declared right here. The model, I mean the data that basically this thing produces to render itself. And that's the key method. So compute state is a method that exists in every computer state component. So that's the data it computes, and we are going to focus on isAnimated property here, or flag. As you see, like the way it produces this flag is First, it gets chat audio state from chat audio UI. Well, basically, it's clear that it's some kind of state that describes what's going on with audio right now. Is something playing, and so on. So as you see, first it checks that like you aren't listening right now, which means that like this button is depressed. Not pressed. And then we get information about the current chat, get last text entry there, see if it's streaming, if it has an audio entry, right? And if that's the case, then we get your own author in this chat and check if the message is basically not originating from you. So if like someone else is talking, then we start the animation. So that's the code. Like, and I think what's unusual here, right, is that okay, like if you have all the data locally, then this code may work, but in reality, it works on the client. Nevertheless, the code is kind of it's weird. It looks like everything is like literally every bit of data exists on the client, right? So why real time is hard? Uh, it's hard not because like just reporting changes is something that's complex. It's hard because you usually have tons of different components, right? Which report the state changes, and in the end, you need to combine a single state. For example, you show the one you show in the UI, and you need to make sure that the single state is eventually consistent. The changes there are displayed in the right temporal order, and so on. And that's the part which is hard to get right. Overall, you need some framework and some set of core principles that allow you to build off that. Otherwise, it's going to be extremely complicated. And let me show you why. So let's say we want to like approach real time like we normally do. So let's say we have an API which returns a single item, right? And we want to render it. And then we want to observe for its changes and render each of these changes, right? So that's the code we probably would write in this case. The only thing that's missing here, I guess, is I forgot to write state has changes somewhere here, right? Well, reality is very different. Like there are many problems in this code, and right now I'll show you some. So first of all, we need to unsubscribe from like receiving changes at some point. So we can do it by implementing IDisposable here, right? And like implementing some sort of cancellation token. We pass to observe changes, which is going to abort in the end and unsubscribe. But like another problem is that we need to call this method first. And only after that, call this one, because otherwise we may miss some changes. So another problem is that this code doesn't do anything in case we disconnect. Basically, doesn't handle the situation with disconnects and reconnects, right? And we also didn't touch the code on the server side because observe item has to be like nearly as complex and as the code here, actually maybe even more, because you may have a mesh of servers on the server side and the state might be actually composed as well. So that's nearly the scenario we have to deal with, right? And what I shown you here is like I didn't even touch the piece where we combine a state from like multiple sources. So even this part, I mean, when we deal with a single source, it's kind of complicated already, right? And these complications or like complexity that we get is what we want to avoid by all means, because like complexity, I mean, it's good to some extent, but like it's well known that that's sort of the source of well, the worst problems you may face in, especially in the kind of second half of a lifetime of any product, and it kills not just products but the societies. So you may find some interesting analysis on this on the web. Okay. So, what is Fusion? Fusion is distributed state management abstraction, which kind of views the whole state of your app as something it manages. That includes the state that's exposed on the clients, on the servers, on backends. Basically, it connects all these pieces together and makes sure that like they get all the updates in real time. Interestingly, it also solves many problems which don't look like even related to real time. For example, caching. Well, and that's because like to have a perfect caching, right? You need to evict the stuff from cache at the right moment. I mean, ideally as quickly as possible. And to have this part, you need something that tells you that like this thing changed. So that's how it's related to real time. Then it's also related to mobile apps and like reducing the network traffic, basically being very savvy on network traffic. Because again, if you know that certain thing still stays the same, you don't have to request it again from the server. It's also related to monoliths and microservices. Basically, it allows you to build a monolith that is extremely easy to transition to microservice architecture. And yeah, later I'll explain why. And like as you saw already, right? Another interesting piece is that like the code you write with Fusion looks kind of almost normal. It looks almost exactly like the code you would write, but without Fusion. So that's the cool part, because it's quite readable, quite clean, and easy to understand. Well, and finally, it's really kind of Blazor friendly. There is a very thin integration with Blazor, but basically it's a natural fit for Blazor apps. And yeah, one of, again, kind of fancy consequences is that you can build server-side Blazor UI and WebAssembly UI or hybrid UI, and it's going to be the same code. Like you don't really need to make any changes. It's going to work. That's how it works in ActualChat and in all Fusion samples. So you can switch them from server-side Blazor to WebAssembly, basically standalone client or client running on the server, and it's the same thing. Okay. So now I'm going to show you one of kind of bigger samples from Fusion. It's called Todo App, and I'm going to basically my goal is to illustrate how all of that basically impacts on certain behaviors of the app. So let's start. Let's start the app, right? So I already have a couple windows open. You see that it just reconnected and I am authenticated here. Well, let's add item 3 and do the checkbox. So you see that basically all these properties, they update. And this one is, by the way, working Blazor server. This one is WebAssembly. Let's switch this one to WebAssembly as well. So you see they work in sync, right? Now I'm going to sign out just to show how it works, and or sign in. So it basically does this in both windows. Okay, sign out. There are two versions of this to-do page, and the version 2 is the one we are going to study. And yeah, let's add one item here for now. So yeah, I'm going to stop the app right now. So let's open these pages, right? To do page 1, and there is to do page 2, right? So what's the difference? The difference here is how like computed state is implemented. You see that on page 1, it basically calls some to-dos service and gets all the items. And the item here is to-do item. If we click on it, we will see that basically it contains everything, right? Then if we go to to-do page 2, you will find out that this thing fetches IDs of the items. And its model, it exposes these IDs. So the code that renders the page uses to-do item view, which gets the ID. If you click on to-do item view, then you will see that its compute state method actually gets the item by this ID and renders it. And as for the first page, it's a little bit different there. It uses a different component to render the item called to-do item row view. And this one doesn't fetch anything. It basically gets the item and renders it. So I think what's reasonable to ask right now is like, what happens under the hood, right? What kind of requests it sends to the server, and like how basically it gets all the data. So we're going to run it again right now. And I'm also going to leave just one of these windows and open Chrome Inspector. Okay. So first, let's refresh the page. Oh my God, that's not to do. Let's refresh the page, right? And how do we clear everything here? Okay. Now let's retry. Okay, so it sends. So it doesn't use HTTP client to send all these requests. It uses custom protocol, and that's why I basically enabled some logging and showing you what kind of calls it makes. So that's the first call. The first call is handshake, right? Then it calls get summary. That's this component, right? Then authentication part, like pulls, I think that's to render this component, pulls some data. You see that get summary now got a response. Then I guess authentication get user got a response. And I think in the end, well, let's focus on list IDs. Yeah, so it, I think all these calls, if you look at the like timing of all these calls, it basically like sends all these calls almost simultaneously, right? And then gets the first kind of chunk of data. Let's add one more item, 2, and I want to add also item 3 and item 4. So let's do refresh once more. So you see that like as soon as list IDs returns the result, it sends like all these get methods, like get requests for the item data in parallel, and like gets the data, right? If you go to page 2 and press refresh, you will, I think, wait, sorry. So you will basically see the same output. So it's like list IDs returns, then it sends a bunch of calls to get the items, right? And as for everything else, so basically it works in a very similar way, right? Okay, so now let's also look at the networking tab, right? And what I want to do here, again, let's clean the log. So I want to show you how basically many exchanges happens here. So these first two are handshakes, then that's the request that combines a bunch of calls and like gets summary data, user data, I think, and other stuff. And this is the request that I think gets all the items. So what's interesting is that, like, from the networking standpoint, it looks like except handshake, just two exchanges. I mean, just two like round trips happened, right? Okay, and yeah, by the way, I'm going to now I'm going to show you the the most optimal version of this exchange. So what I did before running this sample is I disabled one of services here. And basically the service is called local storage remote computed cache. You can click on it. It's implemented right here. It's a very simple service that like basically extends remote computed cache. So you can have a custom version of it, better one than this one. But so let's see what's going to happen once I run the app with this service. So again, cleaning the log, refresh. We need updated client. And you see the first refresh, it's nearly the same exchange, right? So it's basically, let me actually do one interesting thing. So I'll change the protocol as well right now. And we'll use the protocol that at least shows the names of the methods it calls, right? So basically the one that was used here, it's like extremely efficient version, and it uses anyway, that's I guess I'll explain it later, but for now just let's switch it to let's switch the client to a less efficient protocol in terms of like the amount of data it sends, a little bit less efficient. So I refresh and click here. There is literally, so this is a handshake request response, right? But this one, I mean, this message, it combines literally everything. I mean, you see that there is a get summary, get user, and even to do API get methods, like basically get list IDs. So literally everything is combined into a single network packet. And moreover, that's how the response looks like. So the question is like, what's going on, right? How it's possible that this thing literally just makes just a single network round trip and gets all the data. And yeah, let me show you what happens under the hood. So if we go into the application, local storage, so I've shown you that like we now use cache, and what actually happens is that Fusion client basically emulates the connectivity with the server, and like when it gets a request to call one of remote methods, if it has a value in its local cache, then it immediately responds, and at the same time it validates it against the, I mean, basically sends a request to the server, which checks if the value that client has is still the same, and sends back the data only if it differs. Otherwise, it responds that, hey, your data is still correct. Now, let me clear it and just again to show how the exchange starts. So that's what happens when you have an empty cache, right? Basically, it sends the first chunk of calls, the ones it gets all in, like in a single network packet. When you refresh the page, gets a response, and then sends next chunk of calls. Okay. So let's check a few things here. First, let's see if it's going to work if I disable WebSockets. Like disable WebSockets completely. So what? Okay, should be use WebSocket, right? Okay, so we will disable this part, and yeah, let's restart the server. So you see that it's unable to reconnect, right now. Basically, if I click reconnect, nothing happens. It can't reconnect. And if we go to console, then, well, it's going to dump error messages here. But like it kind of pretends like it works. I just clicked here, right? And it can basically run any actions, but nevertheless, right now it's kind of, I mean, let me show you. I can even switch these pages, go to authentication. Like basically it behaves like it works. Let's refresh the page. So I just clicked refresh. It still can't reconnect. It basically, it dumps all these error messages because it can't reconnect. But nevertheless, I still can kind of scroll through the app. And so that's what this remote computed cache does. Basically, it emulates the presence of a server. The server that responds instantly with the last version of, well, whatever data you requested that it knows. On the other hand, since and you will learn about this later in this video, but since everything is designed that basically every piece of data may kind of become stale and report that it has to be updated, then this emulation is possible because, well, literally if server or like if the client sees that the new value on the server is different, like for example after reconnection, right? Then it will run a process that will invalidate it here and like recompute and fetch the new data. So basically, all of this kind of works in tandem with this mechanism that allows Fusion to distribute the information about changes. Okay, let's check one more thing here. So right now, we're going to leave this client operational, and we're going to change the backend on the server side and restart the server. What like supposed to happen, right? Is that like, okay, there is a different server, different backend, so it has to update the data because like it cannot expose these data anymore. Let me do this. So first, let's re-enable WebSockets and run it. I just want you to like see that the client will reconnect in this case, and like basically will continue working as it's supposed to. Just connected, yeah. So the data is there. You can make changes. Now I'm again stopping the server. You see that, okay, disconnected. And so let's replace. So you see that like the service that's I2Do API is the service that is used on the client side, and there is a server for this service, right? So that's how the server is registered. Fusion adds server, and that's the service, and that's the implementation. So we are going to swap it right now with this thing. And so this thing goes to the database, and like it's even more complex than that. And I'm going to like use right now a completely different implementation. And so let's start the server and see what's going to happen here, right? Just connected. So you see that it like refreshed everything right now. Basically, if you look here, it sent all these calls that are necessary to refresh the data, right? And so which one is pending? This one, right? We are looking for. It basically tries to connect, I guess, too many times. Well, I'm not. Okay, finished. Yeah, I'm not sure like how to find the right WebSocket connection now, but I guess it's fine. So the point was that like it changed the state. Okay, let's add a bunch of items here. Well, no, wait. So we need, yeah, we can't use in-memory service for this. It's going to, and so my point is it works, but if I shut down the server, right, then it's going to, the state will be will disappear. So let me quickly get back to the old version. It's by the way, it's wait. So it's a fancy thing. It just reconnected and shown the old state. Yeah, I wanted to show like what's going to happen here. So now the interesting question is, so it sends a bunch of calls, right, when it starts, right? And I think the question is like, if this state is cached, what part of logic is responsible for syncing the cached state. And right now I'm going to show you that like it's okay. So I just refreshed. Oh, by the way, that's also interesting to see, right? So that's what happens in presence of a cache. So you see that like it literally throws every call like in parallel before it even gets the response. So it's like get summary, and it looks here that it sends the get call first. It just kind of goes through first, right? And in reality, it requested this thing. It responded immediately. Then it sends like it requested all these things, and like basically that's how it gets this single packet to send on the server, because like all these calls, they are literally produced synchronously, and they are ready to send basically at almost the same time. So let's just modify the UI code and remove this thing. And I think the expected effect is that we should not see these calls as well, right? So let's do this on to-do page 2, which fetches the IDs, right? I think it's fine. So let's start it. So right now I have to refresh the client, and I click Control R. So you see that there are no calls to both list IDs and get I mean to do API.get. If we go to another version of this page and we didn't modify it, then like that's what's going to happen. It sends all these calls. And if you will go to the networking tab, you may see that I think all these calls were sent. So this is list IDs, get. They were sent at once. And in terms of responses, so they came in 2 different packets, and that's basically depends on the server, right? If server can produce the response synchronously, like because data is available and it does it. Otherwise, it may send a bunch of packets. Okay, so a lot of fun stuff, but I think the main conclusion here is that like it's extremely efficient in terms of getting the data via network, and like even packaging it into basically the least possible number of transmissions. Not exactly least possible, but quite close to that. Okay, now we are going to see how it works. So basically, what is the code that's responsible for all these real-time updates in this app, and like look a little bit deeper. So far we saw mainly the UI code, right? And we are going to look into the server-side code. Okay. So I'm going to basically undo some of my changes here. And what else? Let me see. Yeah, I think that's the only change that I've made. Oh yeah, so like let's keep this protocol for now. So let's start from to-do page 1, the one that basically fetches everything with this call. So what is to-dos? To-dos is to-dos. Let's see how this thing is registered. Right. You can easily see that it's registered as a compute service, which is scoped. Scoped means it lives in like Blazor scope. So basically, it's a client-side service. Like we are talking about the Blazor apps, right? Uh, so and you see that it was registered as compute service, and it also kind of extends this weird interface like compute service. So it's a tagging interface. Well, for yeah, the comment is wrong here, but it's tagging interface for compute service. Yeah. So basically, I think it's a copy from RPC service, requires async proxy, probably from one of these interfaces. But the point is, like, this is a tagging interface. You don't have to implement any methods. It just like tells proxy generator that this thing needs a proxy. And I'll talk about this later. Then, so we were calling this method here, right? And what it does, it calls to do API, list IDs. Then it, for each of these IDs, it calls this method. So basically gets the item. Collect is task one all. Basically, it's like we can rewrite it as task all, something like this. Oh, wait, so it's well, I need to call it here, something like this. So it's the same code. I'll return it back. Collect is just a little bit more flexible thing. So what you see here is that like this thing literally calls to do API and gets all the data from it, kind of rearranges it, right? Packs it into basically a single array or list, right? And returns it. Now, so what is to do API? To do API is an interface. Let's see how this thing is registered. And well, you can find there is a number of registrations, but we need the one that's registered on the client. That's the thing. But basically, it's a Fusion client for this service. If we click on it, then we see that it has, well, other update and remove methods. Like, let's ignore this command handler thing. But again, we see this compute method on get list IDs and get summary. So that's the method that that's basically Fusion method, the method that's kind of backed by Fusion logic. Let's find the server, right, for this client. So I'm going to do the same thing, and that's how it is registered on the server side. Add server to do API. Let's go to the to do API. So list IDs here. It's pretty simple. It calls get folder and passes station here, right? And then calls backend, passing the folder. So you may think of this as a to do API is basically a front-end service, a service that is responsible for kind of rewrapping what backends can provide, but running extra security checks and basically kind of filtering out what you can't access, right? And what it does is like basically, if you look at get folder method there, you will see that it resolves the user from session. And so ignore the tenant part, but I think basically so this thing is going to be empty in this case because we don't run it in multi-tenancy mode. But yeah, this sample can be executed in multi-tenancy mode as well. So this thing is going to be empty, this whole piece, right? And ultimately, it like basically returns a prefix to some key value store, right? Which is either this or that, if you are dependently on whether you are authenticated or not, right? And then for this prefix or folder, it list IDs calls backend method providing this folder. So you can think of it as like basically this part did some security checks, right? And kind of routed the user to the right location on the backend storage, and then like it calls the backend and gets the data. And let's look at this thing, right? So backend is also a compute service. And by the way, let me show you one other thing. Get user is also a compute service. So you see that like nearly every call that I make is a compute service method, or a method that calls some other compute service methods. Like this one, it doesn't have this compute service thing. Oh, let me clarify one thing. So there is no compute service attribute here, but it's inherited from the interface, kind of inherited because it's here. Okay. So the point is, so let's go to the list IDs on the backend and go to, now I'm going to use this very way simpler navigation and just go to the implementation. Oh, and yeah, one of my old breakpoints is here. So if you look here, you will find out that like this code is again like almost normal in terms of like what it does. It basically gets the DB context, right, using some additional service, but ultimately it gets the DB context and then just runs a link query and gets all the keys, right? Maybe by like with some kind of post-processing. What's unusual is, I guess, this part, right? But that's nearly it. So let's. So the question is, right? What happens when we add the new to-do item so that, like, somehow this method gets called again, right? And the answer would be, yeah, let's leave these breakpoints. Actually, let's leave these breakpoints. The answer would be this. So any method that makes some change, it has a block like this, and this block is responsible for running so-called invalidations. Basically, wherever method is called here with whatever arguments passed, the result of this method, if it was cached before, then it's going to be, you may think of it as if it's going to be evicted from the cache. So in reality, it's not exactly like this, and it's a little bit different. But you may think of like what happens here as I just described. Basically, if you call, for example, get summary method with some folder here, and the default is for cancellation token. I just want to show you. So you can remove it, but like it's going to highlight it, right? So, okay. I mean, the writer is going to kind of complain. So let me show you one thing. I'm going to comment out this piece right now. And now when I will be removing an item, summary is not going to update. So since we changed just the server right now, let me see, right? So that's the only change that we've made. Then I I don't have to update the client. Sorry, that's not what I want to show. Okay, so summary. You see that like right now it's updating. The delay there is intentional, so it's not like there is a protocol delay or something. It's basically one of settings. I'm not going to show like, well, maybe I'll show how easy it is to like control all these delays. But the point is, so right now you see that summary gets updated. Now let's try to remove one. And you will see that like it wouldn't change. And moreover, it will never change. Like basically, unless, I mean, I can call like state has changed, invalidate, recompute. I can open another version of this page and it's still incorrect. Because no one told Fusion that summary has to be invalidated. So that's how it works. But if we will add a new item or like edit this one, for example. Oh no! So on edits, it's not going to be updated. But when we add an item, it's again in sync right now. So let me get back to the code that we were playing with. So get summary. I think the reasonable question to ask is like, why there is such a weird syntax and what actually happens? Because it's like, it feels like this code, it kind of cannot run once, right? I mean, it feels like this method runs a number of times, and that's what actually happens. So when this method is executed for the first time, or like when basically the original call is made, it goes through basically this path, and this condition is false. But once it completes and once the transaction is getting committed, and that's why, by the way, it uses a special call here to get db context. Such db context, or like basically it tells that like, okay, this method makes changes and it needs a special db context that is going to be, I mean, the transaction is going to be created there and a bunch of other things that kind of make this machinery work. But ultimately, in the end, when the transaction is committed, it's going to run this piece, and it's going to run it not only on like this single machine, but on every machine in the cluster that like talks to the same DB. So basically, it's like another aspect that kind of helps this distributed mode work. I mean, on the server side, it doesn't even have to kind of sync something over the network protocol, or like basically there is a different approach that allows different servers to invalidate a part of their state when you make changes on one of these machines. And it's extremely reliable. I think, well, I mean, the simple explanation would be that it uses outbox pattern, but in reality, it's like a little bit more complex and advanced. Okay. And yeah, one thing I want to show you is API. So if you like don't involve the DB and use more kind of low level approach, then that's the code that actually allows you to invalidate something. You run this thing in using block, and whatever you call inside is getting invalidated. So in this case, basically, the block like this is executed by one of pipeline handlers for this command. Like any command actually basically detects that, okay, there is an operation that was committed, so I have to run this command again, but in the invalidation mode. That's nearly how it works. Let me show you the last thing right now. So I'm going to run Aspire host for this sample. And it is going to be even more interesting. I don't want to open it here. Okay, let me open it in Chrome as well. Oh, wait, I need this thing. Okay, so right now this thing started like 6 hosts, 3 API hosts on 5005, 6, and 7. And for each of these hosts, it started backend hosts. So backend hosts, they run a backend. API host, they run to do API. And API talks to a backend on corresponding host. So now let's do, well, we're going to close this thing. And yeah. And we're going to go to another host here. So remember, they still talk to the same, they still use the same DB. And what I'm going to show you now is how this distributed invalidation on backend works. So you see that like this is a different front-end host, and this is like also a different front-end host. They use different backend hosts, but in the end they use the same DB. So what's going to happen if I click here? Oh, 6. What happened with this thing? Okay, now let me show you the last piece about this sample. So I'm going to start Aspire host. And yeah, not here, so I already opened it here. Well, yeah, it works. So let me make it full screen for now. So Aspire host started 6 hosts, basically 3 API hosts and 3 backend hosts. And each API host, like this one, for example, running on 5005 port, is talking to this backend and like basically to do API services working here. And it uses backend as a Fusion client. So to do backend, which actually is hosted here. And this service uses this backend and so on. So now, yeah, let's refresh both things. So you may notice that ports are different here, right? Basically, they use different front ends, so the different APIs, API hosts. And these API hosts, they use different backend hosts. And the only common thing they use is database. Are they going to sync? Well, as you see, they do. And that's how this distributed invalidation on backend works. Yeah, they stay in sync as they are supposed to be. So you can switch this to server, like really doesn't matter. what you do. So let's do another thing. So you can find traces here for any host, but I'm going to focus on metrics. And we are going to observe metrics from the let's observe metrics from this backend, and let's go to call duration, call count, right? So list IDs, basically it gets called when we change something, right? I mean, in terms of number of items in the list. Let's, okay, I can't click here. Yeah, so I just removed, we get another call. So the interesting question is, what's going to happen if I click refresh here? That's the first thing. Will it call backend once more? Because, like, I mean, in the normal situation, right? Like this thing will try to get the data and will hit the backend in the end. So I'm refreshing it. Refreshed. It doesn't hit the backend, right? The reason is that like the value that it gets, it's cached on the front end. Let's kill the backend. So we go to resources, post one backend. Can we kill it somehow? Let's try to. Well, looks like, yeah, I can't kill it here, unfortunately. Yeah, I don't know how to like. But my point was that, like, if I kill the front end, then of course it would get the hit on the back end. So I can't show this, unfortunately. Okay, so that's the demo part, and let's move on. So we went through the most complex part, and now I'm going to explain how all of this stuff works. So think about how you build binaries now. Most of build tools like Make, MS Build, .NET Build, wherever, they are incremental builders, which means that they build the final binary by building some intermediates from basically the very low-level inputs like, well, files or like wherever they reference. And so imagine that you change one of these files, right? For example, services.cs. Then, like, whatever depends on this file kind of gets, you may think of like what incremental builder does is that it kind of marks everything that depends on this file as stale or like invalidated. And so, for example, if you want to build this thing, app.exe, right? And it will rebuild server.dll, services.dll, and so basically wherever was like on this path, right? And as for the rest, it will simply reuse that, right? For example, UI.dll is going to be reused. And that's exactly what Fusion does. Like, it might be unclear how it's relevant to what you saw, but Fusion does exactly the same thing, but for your functions. So you like may look at your build process as function calls, like where the argument, like that's the function, right, you call, and that's the argument. And if Fusion gets a chance to transform these functions to such incremental builders, then like you would get exactly the same thing as incremental build. And there is one of samples, by the way, in I think it's probably Hello World sample or something like this. It does exactly this in like, but like simulating exactly this, but on top of Fusion. Yeah, or like, so I think that's the same graph, but with just different methods and different arguments. So that's how Fusion works. And I think the only thing you need to kind of add to, so you already can like build or describe such graphs in your programs, right, by just calling functions. The only missing piece is this like invalidation concept, and I already shown you how it works in case with Fusion. You basically use invalidation block and call functions, which has to be marked as stale with like the arguments you pass there. So that's nearly how it works. Now, yeah, and obviously, like if you think about, I mean, any modern app, then like in reality, you can think of it as you simply rebuild the UI when like by calling functions which call other functions and so on. And so if you have this feature, right, that basically marks certain call as stale, and like you can rebuild the UI. So as a reaction to some change. Okay. So how Fusion works? Well, it wraps your functions into basically a higher order function decorator that adds this incremental build and caching behavior. And a very, very, well, like extremely simplified version of this decorator would look like this. It produces a key from function, and function you call, I mean, and its input. Input includes this and like all the other arguments, right? Then it looks into some cache, trying to get basically a box that kind of describes previously computed value. Let's call this box as computed, right? And well, if it gets one, it uses it. Otherwise, it locks well this key and tries to get it once more. So it's basically a double check locking, right? And returns it if it finds it. But if it can't find such a box, then it basically produces it. And so here, like it basically creates the box, exposes it, and then calls the function that is supposed to compute the value for this box. And so interestingly, if during the computation it gets calls to similar functions, right, and they will resolve with this use or this use or this use. And since we exposed the current box, and basically this thing allows them to register as dependencies in the current box. And that's how it builds this graph of basically cached computed values. Each time it computes something, it kind of updates or like rebuilds the small part of this graph. So in reality, it's way more complex than this. Way more complex because, like, first, well, you can't. It's pseudocode, right? You can't write it on C#. And second is like it's asynchronous. It's truly thread safe, and like many other things. But ultimately, it's basically does nearly this job. Okay, and yeah, if you think of like how, so what happens with these boxes over their lifetime, or like what happens with computations, right? Then so typically you start the computation and get a result or error, and like we can kind of draw separate path for cancellation on .NET. So it's like in reality it's error, but like special kind of error, right? And so with Fusion, it kind of extends this thing. Since this thing produces a box that sits behind the scenes and no one kind of sees it except Fusion, right? Then like basically it returns the value from this box, but the box itself stays. And at some point later, it may become invalidated. So this is a very, very ancient kind of animation that I create on like how invalidation works. So that's why this part it's totally irrelevant. Right now it works a little bit differently, but I think it's kind of good in terms of illustrating what happens under the scene when some invalidation happens and then recomputation happens. So we invalidate like, let's say, like one of low level values, for example, like on backend, right? And it invalidates everything until the front end that depends on it. And then front end like decides, okay, I need to recompute this. And then basically it rebuilds a set of nodes and some of these nodes may reuse other computed values implicitly. So you don't have to do anything for this to happen. But like nevertheless, that's nearly what happens under the hood. Okay, yeah, so we will skip this part because I already shown how it works, and I think we already kind of know what approximately happens when we invalidate or don't invalidate things. Now, one other interesting part is like this Fusion client, right? So you saw that WebAssembly client talks to the server, and servers may talk to other servers. Like, for example, the backend could talk with the front end API service could talk with backend service running on another host. So, and the reason why Fusion uses, basically a special client is that this protocol, and that's the protocol you kind of normally use for like any other RPC service, it doesn't work in Fusion case. And you probably already know why it's not enough for Fusion. So you see that like we throw one message to send the call and throw like the server response with another message and delivers the result. In case with Fusion, there can be a third message called invalidate. Why I'm saying can be? Well, because in reality, I think for a majority of data that lives on the client, it doesn't get it even every session. So just think about this, like most of user data, most of wherever you show, it actually doesn't change. So this part almost never happens in reality. But nevertheless, the protocol has to support this piece, right? And one other important thing is that, like, if you think about this, it doesn't change anything that this piece exists, in sense that, like, okay, you so instead of like one round trip, you get like one plus maybe two transmissions, but in terms of like it doesn't change the big picture basically. And this message is extremely short. It basically tells that the call number 3 is now invalidated. Well, and I think it's worth mentioning that Fusion protocol also supports this thing. It's like it's designed in assumption that the client may have an offline cache for any result it gets. So since this part is kind of is here, right? Then, well, basically when this message goes to the client, it can evict the value from cache instantly, right? And basically, if you don't have this piece, then your client-side cache is kind of useless because it's going to return, mostly it's going to return stale values, I guess, right? And if you have this part, on the other hand, then like it becomes, basically extremely useful. And you still need some extensions to the protocol, right? For example, this kind of response, match response, that doesn't send the data back, right? To make it work. Okay. So, and now I think that's like why this part explains why it's so efficient. So if you think about the call that your client kind of wants to make, right? For example, we want to get an item with certain ID, right? And if we think about the chances of how this call is going to be resolved, then like I think the highest chance is that it's already computed on the client. So basically the value is available, right? Then like, okay, let's assume it's not computed. Then maybe it can be computed from other values on the client, which are already computed. And okay, if it's not this path, then maybe, okay, we resort to RPC, but it can be computed on the server already. And basically the same process repeats on server, and like it may not hit backend server and so on. So that's why, so if you think about this, it's exactly what incremental build does. And that's why Fusion is so efficient in terms of traffic, in terms of like literally everything, in terms of saving CPU cycles, network traffic, literally everything. So it's kind of interesting to think of like how efficient it actually is, right? And like how it translates into a number of calls per second, for example, or so what's the speed up? What's the actual speed up, right? And so there is a test. You can run it. I'll probably run it right now, actually. Let me. So what I want to run, let's run it in Docker. Yeah, this thing is fine. So I'm going to run it right now. Yeah, it's going to build, but let me kind of quickly show you the results. So you will see nearly these results, maybe a little bit less impressive because I'm going to run it with Docker right now, and I'm also recording video. I'm also there's so basically a bunch of things are running on my machine right now. But the point is, so if you have a local Fusion service and if it gets a chance to kind of cache a large percent of method calls, in this case, so this test basically runs a few hundred readers and a single writer that continuously modifies one random item. So I think the chance that it kind of gets basically, if it's about the local service, then most of these calls are going to be resolved from like cache, right? And so when it hits this happy path scenario, then it runs 100. So it's basically something like, I think if you run it on a single core, it's going to be around 15 million calls per second per core. In my machine is more powerful, but it's like, I think 32 cores in reality. So of course it can scale with literally no penalty, but so it's 165 million calls per second. Now the interesting part is that if you are going to use Fusion client for the same service and service is going to be located remotely, then there will be almost no change. The reason is that it just doesn't send the call right when it knows that a given value is still consistent. So like literally it's almost identical number of calls per second, but like when you use a networking client, a Fusion client. And that's why, so you remember the beginning of this talk, right? I was showing you a service from actual chat, like sorry, small UI component from actual chat that renders the listening button. And the code there looks like it uses just local stuff and somehow it works. So that's the reason why it works. The reason is quite simple. Networking services like built on top of Fusion, I mean the services, the networking clients, right, built on top of Fusion, they nearly as efficient as like local services. And I mean, moreover, they also cache the calls. So that's why like there is no difference between using like a service that resides on your machine or resides remotely. And in most of cases, there is like almost no difference. And that's why the whole UI in actual chat is designed like this. It's basically like just throws calls to different services, gets the data, and feels like it doesn't have to do any extra to kind of efficiently process it or react to something. It just like sends the calls and gets the data, rewraps it, and shows in the UI. Okay, so as for like some other results here, so that's so Fusion service versus the same service but without Fusion decorator or proxy, it's I think 1,000 times slower, which is expected because this thing is going to database each time you call it here. Then like a few other interesting results is that like so this is a Fusion networking client, right? A smart client that knows when a value is still consistent and doesn't send the call. So what if we replace it with like less smart client, but based on the same protocol that Fusion uses? So this like I'm going to record a video dedicated to this protocol, basically, that shows how efficient this protocol is. But even here, you can see that, like, if you basically strip off this feature with caching on the client, then it's going to send something like 1.5 million calls per second. And that's 5 times faster than HTTP client would do by querying the same service. Well, and this is the result you would get in like normal case in sense that there is no Fusion client, nothing. So that's what you are expected to have in case you don't add any extras. And by the way, nearly the same, you would get nearly the same output if you would use Redis cache on top of that. I mean, together with this thing, I'll show you why quite soon, or maybe it's going to be in the next video. Okay. So let's see what's the output, right, for our benchmark that we run in Docker. So it's kind of quite close to what you just saw. So it's like slightly lower numbers, but still. Interestingly, that HTTP is, the HTTP client, like just inside the Docker it's marginally faster. Okay, so let's stop this thing. Let me show you one more thing related to our samples, right? So, is it running? Yeah, it's running. Let's run console client for this sample, because it's kind of interesting to see how it's going to work. Will it work? So that's the sample. Oh my god, I want to run it in desktop console client. I want to run it in dedicated, external console. Okay. Yeah, let's. Can we do something like this? Yeah. So since we are not authenticated, I don't have to use any session ID. It's still going to use the same set of items. I mean, the global one, remember. So I'm just, okay, I have to enter something, I guess. Basically, there is some validation logic for this session ID thing. Doesn't allow you to use short IDs. So, yeah, these are our items, right? Let's change something. Yeah, it changed. Let's delete. So it works. Let me show you the client. So as you might guess, it's a very simple app, right? And yeah, this one. Okay. So what do we have here? So session ID, let's ignore this stuff. What we do here is we build service provider by adding Fusion, adding WebSocket client, adding authentication client to do API. So this thing is used in RPC demo part. So we don't need it here actually, and we can comment it out. But the point is so how it gets these updates in real time, right? And then it at some point it calls observe to dos, and you see that what you can do is, for example, you can create a new computed, which is wrapping this computation. You instantly update it because this thing, I mean, this part can be executed synchronously, and to compute something you need to run a synchronous computation, because this thing, all of this is asynchronous, right? So we want basically, if we remove this part, then the first value is going to be output, is going to be the default basically for this thing, and default for the type of what's this? So basically null in this case, right? Okay, and then you can observe changes like this. There are lots of so these the overloads for changes methods and some other. You see that, for example, there is an update delayer you can pass. Let me show you. Delayer get. Well, so this is going to be 1 second delay, and let's also, yeah. Oh, did I click? Oh, stop console client. Let's run it again. So the first update is quick, of course, because we run it explicitly, but let me move it to, so I click here, 1 second later, you see the change here. And that's the power of this abstraction. Basically, it allows you to see things in inconsistent state and know about this. Okay, I guess we are done with this part. like what's the impact of all of this in real apps. And you can find this chart in Fusion repository, I mean on Fusion page, but basically it shows how our actual server responds to one of the most frequent calls at chat get tile. It's basically it returns like 5 messages starting from like certain boundary. So you see that most of these calls are resolved in 30 microseconds. It's not milliseconds, it's microseconds. And like we get timings like 3 milliseconds only when it actually hits the database. Moreover, I think what's important here is that like most of these calls are actually eliminated on the client. So these are the calls that kind of made it to the server. And way more calls, of course, were eliminated on the client because the value was still the same. Okay. Yeah, that's a famous quote on cache invalidation and unsurprisingly naming things. So the interesting piece here is, I guess, that like Fusion offers a fancy solution to this problem. Now, like how many calls are actually tracked in Fusion-based apps? So actual chat is a good example here. And as you can see, like for example, in my case, it tracks, I think, more than 1,000 calls. So basically, these are the values it kind of watches on the server side, observes. And it costs nothing. Like moreover, now I'm going to also show. Yeah, so that's like how the actual cache looks like. It uses IndexedDB in case with actual chat, not local storage, because like local storage is like there are much more constraints, right? But you can see that. So that's for dev instance, and that's why the number of keys is much lower here, but it's still 600 keys. So basically 600 results of calls are cached, right? And this is how actual network traffic looks like. So you see that that's the very beginning of the communication, and the protocol used here is also a little bit kind of outdated. I think I made this screenshot maybe a month ago or so, and I made a bunch of improvements to the protocol. So right now it's much more efficient. But the point is, like you see that like after the handshake, it sends again one big call with like, one big packet which kind of packs a bunch of calls, right? And then like it starts getting so the first response is like almost 5 kilobytes. It also includes the data for like a number of calls. You can see, I think what's highlighted here is that like you even can see by the pattern that probably it's the same method that the same kind of response. And yeah, that's a match response telling that basically, hey, your value that's cached is still correct. So, okay, we are getting to the very final part right now. And there is a bunch of kind of comparison slides for what Fusion versus some more kind of well-known abstractions. So for state management abstractions like Fluxer, MobX, and Redux, and there are many of them, I think the key difference between Fusion and them is that Fusion is distributed, of course. Then it's also thread safe and asynchronous. And that's important because this is what makes Fusion kind of a fit for server-side piece. So you don't have to use it on the client. You can use it just on the server side. And this will speed up your basically API. One other interesting thing is that, like, I think no one does the same stuff with methods as what Fusion does. Basically, this kind of decoration part and implicit caching. Um, yeah, most of these abstractions, they are very explicit in terms of like expressing that you want certain computation to be dependent on like so there are no like methods with you can just call, right? And again, it's quite important thing because that's what makes your code clean and readable. uh, well, as for everything else, I think uh, yeah well, I'll probably skip it for now, but you can read, right? There are of course like many other differences. Okay, now, so what people typically use to address these real-time scenarios, right? And I think one of most well-known kind of combinations is SignalR plus Redis. Um, so why you may want to use Fusion instead? Well, because it's simple versus easy, and I think I'll get back to this part later, and like we'll touch this topic. But the point is, like, Fusion offers a framework, something that like allows you to build well everything in a consistent fashion. Like every piece of real-time logic is going to look the same with Fusion. And as for SignalR and Redis, yeah, you will be basically doing the same, but like each time you are going to solve the same problem again and again. And in the end, like, of course, this approach is way more error prone because all depends on a developer who works on a given part of the app. And if they know how like to do it right, then it's going to maybe work well. But what if they don't, right? And so yeah, and finally, it's kind of it's a lot about reliability, right? So if the framework takes care of like uh, making certain things work the same way, it's actually way better than like when developer, a different developer, each time takes care of the same problem, because like okay, it may be solved in 80% of cases, but like the remaining 20% are not going to work well, and moreover these issues are extremely hard to debug or like even identify. So I think the picture here is kind of shows that like yeah, you can kind of drive on manual transmission, but like who does it nowadays? Um, so, and I think the interesting scenario, or like one interesting case, is like GraphQL and similar protocols, because they sort of, uh, at least the perception is that they can help you to solve the same problem. And well, the harsh truth is that not quite. If you think about what Fusion does, is like in terms of efficiency and so on. Of course, like GraphQL allows you to, well, basically reshape the results and filter out the stuff you don't need. But like each time you refresh the page, each time you start a client, or like even like go to a certain part of UI, maybe sometimes, right? You are going to get this data from server as a single huge box, and that's what's shown on the right side, right? As for the Fusion scenario, you saw that like in reality, first of all, it kind of doesn't need this thing with, well, basically boxing everything into a single box. It does it like completely differently. It allows you to literally like run the computation in such a way that the client, well, just sends a request to each individual single small item. And nevertheless, all these requests go at once. and like literally in a single network packet. And moreover, the response will be much shorter because more likely than not, they are cached on the client. So that's, I think, in case with actual chat, for example, the traffic you get on reconnect is typically just 10 kilobytes. It's like when it reconnects or you restart the app, you get 10 kilobyte of traffic. For the sake of clarity, I think in May, I mean this year, in May, the traffic was about 1 megabyte, and that's before the moment we added this protocol that kind of we added this extension for local caches and stuff like this, and I think that's what you are kind of expected to have with with GraphQL, for example. So yeah, you basically you may optimize things and so on, but like if there is nothing like this, and there is no cache, or if there is a cache that it's not like tweaked for tiny items you fetch individually, there isn't like you wouldn't get the same result. And yeah, that's the scenario. Okay, so there are a few more code examples from actual chat, and I'm not going to I guess cover them in all the details. I'll just show that you can use all of this stuff. So for example, here, this stuff with observing a result of some computation, you see that on line 81, for example, we call computed.new, then create a computed, which basically, in the end, it returns a single Boolean, right? But like it basically awaits when you either leave the home page or your account changes. And yeah, you can like create a computer that computes this value and await for it, and basically create some logic that based on this. So you can observe literally the sequence of. Let me rephrase this. You can await that user of your app takes a sequence of steps and hits certain state, and you can do this because every piece of your UI is like Fusion based. So for example, like service that returns the current user account, right? Or the browser history service. History is browser history service that knows the like where you are in the app. I mean, in which URL and like what steps you took. So basically, if all of this is based on Fusion, then you can just await for certain state to happen. And finally, testing, right? So in tests, you can use this construction, which calls a bunch of compute methods to, again, await when certain assertion kind of passes through. In this case, it's like chat IDs should not contain chat ID, right? So basically, like the list of chat IDs that is produced here, it's like there is no more certain chat in your contacts here. And yeah, this when is going to wait for up to 10 seconds and like recompute this thing every time something changes. And once, basically this thing doesn't throw an exception, it exits, or like otherwise it will fail if it cannot satisfy it in certain timeout. So you can use this stuff in tests. Oh, and that's a very ancient example. I think it's one other trick you can do in all these compute methods. It's like you basically get the current computed and automatically invalidate it after a certain period of time. To make this thing recompute if someone watches over it, right? If no one watches, then okay, you invalidated it, but like who cares? But if someone observes the value of this thing or uses it in some other computed, right, then like they will see the change every second. Okay. So I guess the purpose of this talk was to kind of give you an impression of what Fusion is about and what kind of problems it solves. And yeah, there are probably more questions than answers, but like I think thinking about questions or like asking questions is, I guess, the first step to get these answers, and that's normal, right? So why all of this is so important, in my opinion, because you can rarely get a performance, simplicity, and like low cost. I mean, if we are talking about implementing some real-time stuff, then Fusion is like extremely low-cost solution. I'll show you later like how tiny is the amount of code responsible to for real-time in actual chat, for example. And basically you get like 100x performance, nearly the same simplicity as you used to have without real-time, and like the cost of real-time is nearly zero for you. Okay. And yeah, you saw these numbers already, but that's the speed up you are going to kind of get, right? And that's a visualization of this speed up. I mean, literally a single server may handle a lot that otherwise would be handled by hundreds of servers. And it's crazy, right? Now, like, what are some other reasons, or like what might be some other reasons for you to try all of that? Well, there is a famous Stack Overflow survey. They run it every year. And one of questions in the last one was like, what causes the most frustration for developers? It's easy to predict the number one item, right? And it's the amount of technical debt in like literally every system that lives for like years. That's number one kind of downside, or like now number one thing that bothers everyone. Well, at least like if we're talking about developers, right? So what else developers care about? They want to improve the quality of code. They want to learn new tech, and I'll skip a bunch of items, and they want to contribute to open source. And like think what basically kind of checkboxes Fusion crosses in this case. And speaking of simple versus easy, I mentioned this earlier. There is a famous talk which has exactly this name, or like almost exactly this name: simple made easy. The author of this talk is the creator of Clojure, and it's all about like why it's important to reduce the complexity of your system. So the chart shown here is shows the long-term impact of all these changes. Basically, his description of easy versus simple is nearly this. Easy is what's easy to use, easy to learn, and like basically it requires zero efforts to kind of start to or like basically easy is something that doesn't require you to invest some time to learn, adopt, and use. And on contrary, simple is something that may require decent investment in the beginning, but in the end, it allows you to produce a code that everyone understands, the maintainable code, the kind of code that's easy to read. So obviously, yeah, you can basically, I think, and it's also a lot about the level of abstraction, right? So simple can be of a higher level of abstraction. And that's why it requires you to kind of invest into studying it or like using it. But like easy can be like easy, so no investment. But the problem is that like basically if you use these like low level abstraction things, right, then you will quickly get into a state where you're like the system you build becomes kind of unmaintainable and hard to evolve. Okay. And I think this illustration is a good example of like what level of abstraction means, or like what I guess simple versus easy means. So if you don't know about async await, then the code on the left looks perfectly fine for you. Like you may even think like, okay, probably there is no better way to do that, right? And on the other hand, if you know about async await, then this code looks kind of dumb, right? So speaking of Fusion, that's what that's nearly what it does with your code. It's like, yeah, it's well, probably even better because like in reality, your new code looks almost like the code you would write otherwise without any real-time stuff, caching and blah blah blah. Okay. Uh, so what's the cost of like using Fusion and the cost of, well, basically building real-time app on top of Fusion? So if you look at the bottom part of the screen, you will see that I was searching for if invalidation.is, right? And basically, I counted the number of invalidation blocks in actual chat. So the total number is 90. It's like 90 blocks. And I think the total number of lines of code is something like, well, I don't remember exactly, but probably like 200,000, something like this. So it's a tiny, tiny percent of code, like literally tiny percent of code that makes like probably like almost the whole real time. So at least, except maybe some rare parts, it's like what uh, allows actual chat to display changes in real time. I think I also remember that like I wrote a smaller sample, but kind of close to real life as well, board games. And the number of invalidation calls there was around, I think, 30 or so. So the invalidation blocks. Basically, like the delta between an app you can write in like a week or so and an app that you like your team may spend like years on is like not that big. So what are some other benefits of Fusion? Well, that's one of such benefits, right? Typically, you can't have the same code for implementing Blazor server app and Blazor WebAssembly app, but not with Fusion. With Fusion, it's exactly the same code. I already mentioned that, but the same is applicable to monolith versus microservice scenario. And again, it's the same thing. If every service you build behaves nearly the same way, whether it's local or remote, then like what stops you from turning a system that is completely local, like running on a single server, into a distributed one? Nothing. So, and yeah, speaking of like many other evils you may face, otherwise there are plenty of them. It's well, literally a plethora of tools that may help you to implement real-time behavior or caching or wherever. But the problem is that like you need to learn all of them, like all of them in most of cases, and all of them have their own issues and so on. And even if you think about like such simple scenario as UI, for example, right? With Fusion, you don't need any extra on UI because like the abstraction works everywhere. On UI or like on like server side, it's the same thing, right? And if you don't use it, then you need something like Fluxer or whatever. And the same the same is applicable to caching, and the same is applicable to some like transmission protocol like Signaler and stuff like this. And like you really need to kind of learn all of that and tackle problems associated with any of these tools. So, okay, we are getting back to the repository slides, I guess, which means that we are almost in the end of this talk. Yeah, that's the URL you need to learn more about Fusion. It also would be great if you put stars or like watches, like forks there, because that helps us to like grow. There is a dedicated repository with samples. There is a there are lots of them. I'll probably show you the last one. Well, I'm not sure. Maybe next time. So, yeah, that's almost the last slide. So it's a famous scene from Matrix movie, and the reason I put it is probably straightforward, right? You may of course, like forget about all of this and like stick to the conventional tools, stick to what you know, but probably know where this road kind of ends, right? And basically, Fusion is something that's completely different and completely new. So that's the final slide. Thanks for like watching. I know it's a pretty long talk. And yeah, I think couple other things to mention. So if you want to ask some questions, go to, actual chat and just either ask in Fusion place there or feel free to bother me. There is a decent amount of documentation, but I think there are lots of ways to improve it. So that's where I guess I would love to get some help. Plus, if you want to extend Fusion or bring Fusion to some other language, I think that's one of the areas we can try to work on together. So if you find all of this interesting, then definitely feel free to reach me out, and yeah, I'll be happy to help. Thank you.